Hello, welcome back. Revision for year 13's trigonometric identities and proving in particular. I think the last time we reached up to question 21. That was on the lecture number 2. We're going to go to lecture number 3, starting with question 22. And I got 40 altogether. Probably we'll have to go over 4 lectures. So I hope to do as many because now the question will get a little bit more demanding and they will take it slightly longer. So we'll start with 22. I'm going to put the list up there, and without wasting any time, you know the setup for this type of questions. Question 22 says to prove that two lots of the cot of 2 theta plus the tan of theta plus tan of theta, we need to prove that it's identical to the cot of theta. I think I've done something similar, or possibly a rearrangement of that, kind of like rings a bell earlier on. We're going to start, of course, with the left-hand side. And what do we do with something like this? Quite clearly, we need to break this cot of 2 theta. Do we go sines and cosines, or do we stay with cots and tans? Both of them will work. The only problem, if you stay with tans and cots, for the majority of students, is you're not likely to know or remember your cot double angle, which is basically your tan of 2 theta turned upside down. You're not likely to know, for example, that the cot of 2 theta is equal to 1, if you write in terms of tan, that is, as 1 minus tan squared theta over 2 tan theta, and then of course proceed from there to finish off. So we'd probably be a safe bet to go sines and cosines. So 2 sine of 2 theta, sorry, I'm writing stupid things. That should be a cot, so I'm writing a tan there. Cos of 2 theta over the sine of 2 theta plus, of course, the tan of theta. And we're going to see how we're going to simplify that. Break this double angle. First of all, the denominator, we have no choice. We have to write it as 2 sine theta cos theta. And of course, this will cancel the 2 at the front from the 2 cos of 2 theta. How are we going to write now our cos of 2 theta? There are 2 versions. Don't know how much space I'm going to need. Which one is the one that we need in there? It doesn't really matter. If you're unsure, let's clear that a little bit and then we'll take it from there. Personally, for something like this, I can see probably the better one. It might be, we're going to split the fraction afterwards. It might be, let's go for this one. We haven't actually used it for a long time. Cos squared theta minus sine squared theta. They will work either way. Okay, plus the tan of theta. Cancel your 2's and then split your fraction. Cos squared of theta divided by sine theta cos theta. This will produce tans and cots really. Minus the sine squared of theta divided by sine theta cos theta plus that tan. Somehow we need to lose that tan of theta at the end. Some cancellations. Cos gone, squared gone, so that would leave me the cot. That's a cos of a sine, of course. Minus sine, goodbye, squared's gone, sine of a cos. This is of course a tan plus a tan. I don't even want to write this because I have to rub it off in 10 seconds. Is equal to cot theta, which of course is equal to RHS. It wasn't that bad, was it? Number 23. Very different style, number 23. Lots of squares there. We have to prove that 4 times the cosec squared of 2 theta minus the sec squared of theta is actually equal to the cosec squared of theta. Okay, definitely left-hand side. Again, a lot of stuff happening in there. But the question is, what do we do next? We got the choice of 2 there. I can see the difference of squares. Not a lot of people will be going for this, and probably I won't go for that either, because that's 2 cosec of 2 theta all squared, and then we get 2 brackets. But then I'm still going to have the 2 theta in there, and I got 2 brackets to multiply out. Do I like this? No, I don't like this. So what is a sensible thing to do? Lots of squares in there, possibly we'll go to some kind of Pythagorean identity setup, but I need to concentrate on this 2 theta. I need to break that down first. So the first thing, I'm going to switch into sines and cosines. So 4 over the sine squared of 2 theta, so that's this bit here, minus sec squared of theta. And now we have to be a little bit careful with this particular one, because we've got the 2 theta and the square, and can easily go wrong. I'm going to put an extra line for this. So first of all, you need to remember that the sine squared of 2 theta is the same as the sine of 2 theta all squared. And this is, of course, 2 sine theta cos theta all squared, which, of course, it will give you 4 sine squared theta cos squared theta. Often with this kind of manipulation, students somehow miss a factor of 2 from there. If there's too many things happening, it's very easy to miss it. Okay, so I've essentially done that there. So this I can actually borrow the answer now. 4 sine squared theta cos squared theta. And the sec squared, it makes sense. We have sines and cosines, so let's write at the same time to that. Okay, what happens there now? The 4's can cancel, no problem. Is there a lot of things we can do in there? Clearly not, apart from a common denominator. So if I multiply top and bottom of the fraction on the right by a sine squared theta, I'm going to get a common denominator. They both are going to be out of sine squared theta, cos squared theta, and on the top I'm going to have 1 minus sine squared theta. And now it's time to start smiling, because we are done practically. 1 minus sine squared theta. I often give the answers. Cos squared theta over, lucky that wasn't anything hard to see. Everybody should be able to see this one. Okay, this cancels, and that gives me, of course, 1 over sine squared, which of course by definition is cosec squared theta, which of course is our RHS. And this is number 23 done. Number 24 looks quite messy, a lot of stuff there. A fraction with loads of stuff on the top and on the bottom. Having a lot of stuff doesn't necessarily mean it's hard, actually. So let's not panic. 23, 24. I'm going to move out of the way. Sine 2x plus sine x. Sine of 2x plus sine x. Quite clearly, we need to break that sine 2x at some stage. And at the bottom, I've got a cos of 2x plus a cos of x. Just checking the signs, pluses, yeah, plus 1. And apparently this simplifies, is identically equal. And I should have written here identically equal, because an identity is not an equation we're solving. That in fact is equal to the tan of x. Okay, what shall we be doing for this? Well, it's quite obvious. We have to do step at a time, and the thing that really needs doing in there is to break your double angle. We got double angle in 2 places. The right hand side's got just x, so clearly the 2x here and the 2x there needs to go. So we're going to start with left hand side. On the top, no choice for the sine of 2x, it's just 2 sine x cos x plus the sine of x. And at the bottom, I'm going to put a bracket. That is going to be whatever I choose to change my cos of 2x. I've got a choice of 3 there, plus the cos of x plus 1. And if you look a little bit ahead before you make that decision, probably the one that you need in there is the one that's going to cancel this one. Okay, because you got 1 minus 2 sine squared or 2 cos squared minus 1. But I also observe on the top, if I factorize the sine, sometimes it's worth looking at things ahead, looking at your answer, the sine of x, I'm going to get 2 cos x plus 1. That's on the numerator. And I'm looking at the tan, and the tan, of course, not that equal, and the tan is, of course, a sine x over cos x. So this will be created possibly on the numerator, and then I will have the sine. So somehow I need to cancel perhaps this bracket from the bottom and end up with just a cos x somehow. So that's something to keep in mind. I'm going to leave it there just for reference. And let's concentrate on the cos of 2x. Let's try to get rid of this one. If it doesn't work, we'll try something else. So I'm going to write 2 cos squared x minus 1. That's your cos of 2x. And I'm choosing this version because I got minus 1 plus 1, so it will cancel. What happens next? Let's look on the denominator before we decide what to do with the numerator. In other words, shall we factorize it? The ones will cancel. And I'm going to have a 2 cos squared x plus cos x. Again, I'll be able to factorize the cos out of that and that to leave me a 2 cos x plus 1, and this is in fact what I was suggesting when I looked at this. So now we can actually factorize the top. On the top we're going to pull a sine, so we're going to have 2 cos x plus 1, boom boom, equal to tan x equal to RHS. All done. Question 24. It wasn't actually as bad as it looked. Okay, maybe we're getting a little bit better as well. I'm certainly getting better at this because I haven't done trigonometry now for a little while, since the middle of last year, this kind of stuff. So you become more fluid, of course, and more fluent as you do stuff, because now the year 13s started getting back into this kind of work. So I'm doing a lot of this all the time. Number 25 is actually a very bizarre identity, but it's actually very standard, and you ought to know how to prove it. I use it often in my work, and in exams it makes its appearances every now and again, and you need to learn how to do this particular identity because it's not obvious where to start. If you were to go through the normal routine, left hand side or right hand side, common sense dictates go to the bits that you got a lot more stuff of in order to simplify. But the question is 4 cos cubed x minus 3 cos x, now what? And more importantly, how will you know that you ended up now with a cos of 3x? I mean, I don't know nothing that involves 3x. It's the first time, obviously, I'm dealing with something like this. So in fact, for this particular one, and often in exams, they will give you a clue for this one, more likely than not, is to actually write your cos of 3x as the cos of 2x plus x, in order to use your compound angle identity for a plus b, where a is 2x and b is just x. So that's cos cos sine sine with a minus in the middle. So cos 2x cos x minus the sine of 2x, the sine of x. That's the cos of a plus b used with these values. Okay, next step. Of course, if we look on the right hand side, we only got x's. So it's quite obvious we need to break the 2x and the 2x from there. Okay, where do we go? For this one, it's of course a very straightforward choice. The only thing we know is 2 sine x cos x. The question is, which version do we put for the cos? Because everything is in cos here, it makes sense to write 2 cos squared x minus 1. I hope you know all your identities, or you've made the reference sheet so you can look at them as you're using them and learn them in the meantime. So that's the cos of 2x here times the cos of x minus 2 sine x cos x. That's of course your sine of 2x multiplying another sine x, and I'm going to do a tidy. Multiply your first bracket. We're going to get 2 cos cubed x minus, what x is that? It looks like a p. All right, 2 cos cubed x minus cos x, still on the multiplication of that. And then I'm going to get minus 2 sine squared x cos x. Are we getting there? We got x cos cubed, we got cos x. We got this lump here, which is a little bit different. It's got the sine squared, but of course sine squared, we can change it into coses very easily by using the standard year 12 identity that says that your sine squared is 1 minus the cos squared of exactly the same argument. So we got that. So we have to be a bit careful now with the tidy. For this particular one, sometimes it can confuse. Hopefully it will not confuse us now. So you can think of that, and you might want to rewrite it just to actually see what's happening in there. It's that times that times that, and then is that times that times that. But it's probably better to actually, I'm going to write it here actually, 2 cos x. So I wrote the cos x after the 2 and then my bracket. So it's actually easier to follow because it's much nicer like this. So we're going to get, of course, a 2 cos x. Don't forget we got a minus there, and then the minus times the minus will give you plus 2 cos cubed of x. And if we look at what we got up there, we got 2 and 2 of those, 4 altogether, cos cubed of x minus 3 lots of the cos of x, which of course is equal to RHS. Please make sure you know this particular identity, as I said, is coming up at regular times, and of course its cousin, and its cousin of course is the sine of 3x, which is very, very similar. It should read 3 sine x minus 4 sine cubed x. Okay, so I'm not going to do this one here. When I decided which questions I will put on this lectures, I had to make a choice between sine 3x or cos 3x. I picked the cos. There's no need to do both, of course. Once you know one, the other one is very similar. Number 26 looks like a tedious one. We need to prove that tan x over sec squared x minus 1, yeah, minus a sec squared x minus 1 over tan x is equal to, or identically equal to be correct, 2 lots of cot x. I think I've done this question with just different trig functions. A lot of them are symmetrical. In other words, if you replace, I don't know, tans for cots, secs for cosec, there, I don't know, you might get a 2 tan or might be a minus, or if you might need to switch that into a plus. They have exactly the same technique. So it's basic regurgitation of the same stuff. I've done one of these already in previous lecture. I can't quite remember which one. So for something like that, left hand side, and we got a choice there to either add the fractions as they are or switch into sines and cosines, tidy up your double fractions, and then go ahead. Personally, I will probably add the fractions as they are, okay, for this one. So let's make a common denominator. Common denominator is going to be out of tan x bracket sec squared x minus 1, and then we need to times the tan of x by another tan of x, so it's going to be tan squared x, or if you want, multiply top and bottom of this fraction by tan x, minus, we have to be careful for this particular one because of the minus, bracket sec of x minus 1, and times it by itself again, squared, or if you want, times top and bottom of this by sec x minus 1. Extra careful now on the numerator. this we can multiply it, or we might leave it as it is. That's how I remember this particular question. I said I've done it before. Look at your answer. Your answer is 2 over tan of x. This is our target. Okay, here it is. There's a 2 that's missing on the top, and we got this. This probably will cancel, so we need to leave that tan outside that bracket. Okay, so I'm not going to multiply. I can if I want in the future. And even if you didn't see that and you multiplied it, please remember where it came from later on, so you can refactorize it back. Tan squared of x. You have to be a little bit careful with that. Put additional workings if you're not feeling confident. I'm going to square the brackets and take care of the minus at the same time. So square the first quantity, sec squared of x minus sec squared of x. Multiply together and double, minus 2 lots of sec x plus 2 lots of the sec of x. Square the second bit, positive 1, minus 1. Okay, so this is now what we have so far in this particular line. Okay, we got tan squareds and sec squareds in there, and let's look at this. This is quite interesting. This sec squared x, 2 lots of sec squared x minus 1 that I've got in this particular line in there. Should that perhaps cancel with something at the bottom? Because I do have, no it doesn't, that's just a sec of x. Okay, so let's wrap that off and let's tidy this top. We're using the identity 1 plus tan squared x is equal to sec squared x on the numerator. So the question is, do we change the tan or do we change the sec in this particular case? Okay, what we're going to change in this particular case is, so we go for the tan squared. So we got tan squared of x is equal to sec squared x minus 1. Okay, let's see how that changes things. Sec squared x minus 1, so that comes from the tan of squared, sorry, not tan of squared, the tan squared of x, I beg your pardon, minus the sec squared of x, that's this bit here, plus 2 lots of the sec of x minus 1, so it's my new numerator. And let's leave the denominator as it is in factorized form, sec of x minus 1, and let's do a tidy. What happens in there? Well, quite clearly the sec squareds will cancel. We got that's gone and that's gone. Do the ones cancel? Unfortunately not, but is that bad? Let's have a look what we got remaining in there. We're gonna have the 2 sec x, so let's write this first. 2 sec of x minus 1 is minus 2 over, and I'm missing an x in there. I wrote tan without an argument. I should give myself a detention for that. Tan of x sec of x minus 1. Okay, now I think we can see where that is heading. Factorize your 2. Sec x minus 1, and of course our denominator, as we were planning, as we just looked ahead, look what is happening out there. The bracket, as we predicted, perhaps it was going to cancel. Took a little while, a bit of work there with the identities, and then of course we got 2 over tan x, which of course is 2 cot x, which of course is RHS. That was quite demanding. We are now getting towards the middle of the identities, that the ones I plan to do. So questions will get a lot harder now and a lot more lengthy in the proof. But I hope you are following what is going on. And I need to remind you that this is not the kind of thing you just do in one day and you're done and you say, look how good I am at this. This will take a very long time. I advise you to be working slowly, perhaps devote, I don't know, half an hour to 45 minutes at regular intervals. A regular interval does not mean once a fortnight. For this kind of work, regular intervals is something like every other day, if not every day, in order to familiarize, first of all, with the important identities, and also being able to see techniques, patterns, and all sorts in this kind of work. Okay, this particular question, it has sentimental value. Is one I wrote for an exam board a very long time ago. This is in the 90s, and it was done for the Northern Ireland, for the what is now called CCEA. Okay, very, very long time ago. It's one of my first contributions. How do you simplify this? Well, we're going to start clearly from the left. Left-hand side is equal to. Okay, loads of stuff, sec, cos, cosec, sine, and on the other side tan. The only thing that's missing from this is a cot. All right, sensibly, probably switch into sines and cosines. We cannot split the fraction there because, of course, we've got two terms on the denominator. There's no other identities. There's no double angle. So all we can hope for is to write this as 1 over cos minus a cos over 1 over sine minus a sine. And now the question is, what next? We have a double fraction. We can put these two things together, and go for a long ride, and eventually and hopefully rather, get to our answer. But I'm going to do this a little bit more advanced. First of all, if you do it the long, hard way, I'm just putting some very fast workings there. 1 minus cos squared x over the cos of x, that's the numerator, over 1 minus sine squared x over sine of x. And your answer to this will be the product of the outer terms on your top, sine of x, 1 minus cos squared of x, and the product of the inner terms is going to be your denominator, 1 minus sine squared of x. And of course, this bit here is a sine squared, this bit here is a cos squared, and then sine cubed over cos cubed, which is your tan cubed. But we're going to do slightly different here because I really want to emphasize a technique that I use in a lot of the work that I'm doing, which is to multiply top and bottom of fractions with certain quantities in order to simplify. This is a little bit of a beastie, so I'm going to put full working so we can all follow what I'm doing. I want to clear all of this. On the denominators within the double fraction, I've got cos and I've got sine. So in order to clear all the denominators, I need to multiply by the product cos x, sine x. I'm going to use different color pen, and I'm going to put full workings, so for the benefit of everybody who's trying to follow this. Otherwise, you do something like that in your own time. Cos x, sine x, minus. There's the cos of x, and I need to multiply this term as well by cos x, sine x. Then at the bottom, I'll go 1 over sine x, which of course it also needs to be multiplied by cos x, sine x, and lastly minus the sine of x, which again it needs to be multiplied by the same quantity. If you multiply top and bottom of a fraction by the same non-zero quantity, then you don't alter the fraction. You're getting an equivalent fraction. Why I've done that is because I'm going to get sine x minus cos squared x sine x from this term here. There I'm going to lose the sines, so I'm going to get a cos of x minus sine squared with a cos of x, so sine squared cos of x. I'm going to move up here, so I had to go through the workings in there. If you look on the top, I can factorize the sine of x bracket 1 minus cos squared x, and I hope you remembered what I've just written up there. which are now rubbed off, I had exactly the same line. And if I factorize a cos x from the denominator, the cos of x, have a look at it once I move out of the way, cos x and cos x pulled out, 1 minus sine squared x. This is, of course, your sine squared. This bit here, that's sine squared, so sine cubed now altogether. And this, of course, is your cos squared. So altogether, we're going to have a cos cubed, which, of course, equal to the tan of x cubed, which, of course, is R8s. Okay, you might think, okay, I didn't gain a lot by doing it like this. Perhaps I should have done it the other way, which perhaps is safer. But keep in mind, somebody who is competent in this particular manipulation doesn't even need to write this line. This is the line that just took ages to write for us to see. It can go from there to there, and then it's just very, very quick to the end. Okay, so that was question number 27, or identity number 27. Let's switch page and look at number 28. 28. Let's see how far we can take it today. The cosec of 2x, is identical to. Didn't we do this today? Cot squared x. Let me just write it down first of all. Cot squared x. I think I've just done a minute ago or something. Maybe I'm remembering something else. I just have to flip the page over just to double check, because this reminds me of something. No, it's not. How strange. Okay, I would have sworn I've done this one. Okay, left hand side or right hand side? Well, we can do it from the right hand side by switching to sines and cosines. We can also do it from the left if we're showing off. How can we do it from the left by showing off? While I'm rubbing the board, some people perhaps can think ahead. You're going to write this as 1 over sine of 2x, and then 1 over 2 sine x cos x, and then of course your sine at the bottom requires splitting. But what about this 1? You're going to have something like this. What about this 1? Well, this is not a 1. You thought it was, but in fact it is a cos squared x plus a sine squared x. The problem you're going to have is to know when you're done on this. So where do we go from there? If you look carefully, you see that 2 there and that 2 there. We got plus, we got cot squared. Cot squared is cos squared over sine squared. If you quickly divide by sine squared all the way through, you get your identity. This is not something which is natural. I just thought I'll mention it because the identity is written with this bit on the left. We're going to do it a little bit more sensibly because we have to be sensible, and we're going to start with the right hand side. Okay, right hand side, we're going to do what? First of all, 1 plus cot squared, is that an identity? It rings a bell. Yes, it is. It's in fact equal to the cosec squared of x. If we spot that, we can write straight away cosec squared x over 2 cot of x. What do we do next? We'll probably switch into sines and cosines. What do I do with this 2? Let's leave it more here for the time being. So that's half. Let me put an extra step, cosec squared x with a half. And this cot, I'm going to shift it to the top, but now it changes name to a tan. So this is now what I've done so far. Then sines and cosines. So this is equal to 1 over sine squared x, that's my cosec squared, and of course the tan is sine x over cos x. Goodbye. Is that good? Of course it is, because of course this is 1 on the top, 2 sine x cos x, which of course is 1 over the sine of 2x, which of course is equal to the cosec, not cosec squared, cosec of 2x, which of course is equal to the left hand side, because we started from the right. So that's if we spotted that it's an identity. What happens if we didn't spot that? So, because some people, they might just not have seen that. Is there a way we can do this without switching the top? The answer is yes. If we just go straight sines and cosines from the very beginning, I think it's going to be just as good. There's your cot. Cos squared x over sine squared x plus 1. That's the numerator. And the denominator is 2 cos x over sine x. I'm going to clear that on the next line by multiplying top and bottom by the same quantity. I've got 1 lump, 2 lumps, 3 lumps, all to be times by the same quantity. The question is, what is it? And I'm not going to put workings, I'm just going to write the answer. The quantity that I need that will clear this is actually sine squared, because I got sine squared here. So picture sine squared next to each of those. Sine squared there, boom, boom. Cos squared. 1 times sine squared, which of course that will give me 1. And if I put a sine squared here, it will cancel that, but it will only cancel the sine squared. I'll still have a sine. So this will give me a 2 sine x cos x. Okay, that I shouldn't have written, I shouldn't have crossed it out, I've just done that so you can see what is going on. And of course this is going to be 1. This is going to be the sine of 2x, which of course dot 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 equal to the left hand side. So this just works just as good. In fact, probably if it was me, I would have gone for this particular version. Okay, question 29. Question 29. Again, didn't we do this today? No, we've done his cousin. It's practically the same thing. It's what I was just saying. If you look at number 23, if you go the video back, or if you're writing things down, well, it's just the same identity, really. I'm gonna skip number 29. I'm gonna tell you, I'll leave it for an exercise. It's just very, very silly. If you look at number 23, it's practically the same thing. So it's this number 29, 4 cosec squared of 2 theta minus the cosec squared of theta is equal to the sec squared of theta. This is the same as number 23, really. It's not any different. I didn't spot it, so I'm going to skip it. You can actually try it. It's not that it's still good practice. Okay, and we're going to look now at the next example, number 30. Again, we've done something similar already. So this identity is 2 fractions subtracted, sec on the top, sec x and sec x, and on the bottom we got 1 plus the sec of x and 1 minus the sec of x. And apparently all of this is equal to 2 cosec squared of x. So this is the identity number 30. Quite clearly left hand side. What do we do in there? There's a couple of choices. Of course we can just add the fractions as they are. We can switch into sines and cosines first, but also we can actually factorize on the left hand side. I can pull a sec and a sec out and have in a bracket 1 over that minus 1 over that. Does that give me a huge advantage? The answer is probably not. So the best way perhaps for this is to just add your fractions. I think that will do just as good. So put the common denominator. 1 plus sec x multiplying 1 minus the sec of x. And on the top, the sec of x is to be times by bracket 1 minus the sec of x. Careful with the minuses there. You have to be careful with identities like this because it's very easy to make mistakes on the signs and cancel the wrong things. So I don't need the bracket in there. For that is minus the sec of x, that was already there. And I need the bracket now because I need to times it by 1 plus the sec of x. Do I times this denominator? This will probably produce an identity because it's a difference of squares. So you're going to get, of course, 1 minus sec squared of x. You can do all the workings. And I'm going to write it up here. 1 plus the tan squared of theta is the same as the sec squared of theta. So at the moment we got it with a negative. So if I rearrange it as 1, bring the sec to the left, sec squared theta is going to be equal to minus tan squared of theta. So that might be useful. Let me just leave it up there because at the moment I'm not quite sure if it will be useful like this or I might cancel a bracket. So this is definitely the same as that. At any stage I can just replace it. Let's tidy the top. So the top is going to be a sec x minus a sec squared of x, and then I got another minus sec x, and then I have another minus sec squared of x. So what happens there? What do we cancel? We cancel not the squares, we cancel the ordinary secs. So we're going to have two lots, negative 2 lots, minus 2 sec squared of, I was going to write theta there, sec squared of x over 1 minus sec squared of x. And the minus there is quite convenient because now we can actually make this into a minus and this into a plus. So shall I put now the equivalent of that? The answer is clearly yes. So we're going to write as minus 2 sec squared of x, that's the numerator, over the 1 minus sec squared is equal to minus the tan squared of x. We need it in x, of course. So now the minuses will cancel. Shall I make some space? I don't know if you can see the board on the video, so I'm a little bit concerned that I might be writing and you can't see what I'm writing. The minuses will cancel into a plus. And then what is probably the best way of doing this is to write it as 2 sec squared of x, the tan squared, move it to the top as a cot squared of x. And I'm going to have to rub off stuff. We lost the space by leaving the number 29 up there. So I'm going to use that little bit of space. I'll write it in blue color. So the continuation now is here. I'm going to switch into sines and cosines. 1 over not theta, cos squared of x, cos squared of x, that's this bit here. And the cot, of course, is a cos squared x over sine squared x. And the result should follow because we now have 2 over sine squared. And the sine squared at the bottom is, of course, 2 cos x squared, which, of course, is equal to the right-hand side. So this was, it had a little bit of work to do, actually. It wasn't as straightforward as another one that we've done a little while back that he had to add fractions. Okay, so I would go for number 31 and 32. I think that's 2 more for today. I'm trying to make sure we fit all the questions into 4 lectures, and I try to keep it roughly the same in length. I do apologize if I'm overrunning a little bit. So, oops, number 31 is not too long. 31 says, we've done this one already. It's just that it's dressed in different clothes and you might not recognize it. We need to prove 1 plus cos x over 1 minus cos x is identical to the cot squared of half x. The first time you see things like that is a little bit scary. We don't know how to, we've never really seen identities half x. So how do we do something like that? People that are able, they don't really need to do anything. They can write the identities required straight away and manipulate it. But I will advise, if you have a situation like this, the problem is quite clearly this item here, half x. I don't like half x. So call it theta. So theta is in fact half x, or equivalently x is equal to theta. Then the identity will be proven so long as you prove that 1 plus the cos of 2 theta over 1 minus the cos of 2 theta is identical to the cot squared of course, theta. And the way you do this, if you start from the left, we need to get rid of these ones, so we need to use the double angle for cos that destroys the one that's there. So for this one, and let's put 1 minus, we need the 2 cos squared theta, 2 cos squared theta minus 1, and for this one we need 1 minus 2 sine squared theta. What will happen on this occasion? 1 and minus 1 will cancel to give us 2 cos squared theta over 1 minus 1 cancels. This will go plus 2 sine squared theta. The 2's will cancel. Cos of a sine is of course cot squared of theta, which of course will be your RHS, and you can make reference of course to the fact that this is the substitution. I'm not going to show at the moment. Basically you can write it. I've just a little mention. Please, if you don't follow what I'm doing in next, I'm going to do it very fast. Please just ignore what I'm writing for this. 1 plus cos x over 1 minus cos x. This is double angle. You might say to me, there's no double angle. Of course, there is double angle there. You can make double angle out of anything, even if you had cos of 0.25 of x. So 1 plus, you're going to write it as 2 cos squared of x over 2 minus 1. The double angle is just a doubling half relationship. And at the bottom, you're going to have 1 minus 2 sine squared of x over 2. The ones will cancel, so that you will leave you just this positive over this positive. The 2's will cancel, and then you're going to have a cot squared of x over 2, and you don't need a substitution. But I would advise for the majority of us that are sitting just the ordinary A level, if you get something like that has half x in there, please just use a substitution and change your half x into whole numbers, or not whole numbers, whole quantities if you want, whole variables, because it'll be easier. And we're going to finish with number 32. Number 32, so this lecture will go 22 to 32. And 32 is, I'll just glance at it, is one which is very simple to prove, but very difficult to actually see how to prove it. Let me just write it down. 1 plus sine x, 1 plus the sine of x over the cos of x is equal to the cos of x over 1 minus, identically equal to, minus sine x. Okay. You might be able to actually see a couple of things, although this is not the way you'll be proving something, because of course you can't just be using this as it's true and then taking your answer basically and using it. But you should be able to see, if I multiply across, that's cos squared, and this times that is 1 minus sine squared, and of course that's true. But I don't want to do something like that. It's me personally, I wouldn't accept that. I might give you a mark for spotting something like this, but in a marking scheme, but I will not really give you the marks for this. The question is, do we start from the left or from the right? The answer is, it doesn't really matter. This is symmetrical, and you can start from either, and you can do analogous workings. Here is now one version that starts from the left. Left hand side. What do I do with this? There's not a lot of things we can do. I guess we could split the fraction. We can write it as 1 over cos, which is a sec, plus sine over cos, which is a tan. But I don't think that is a sensible thing to do. What is more sensible thing to do for something like this is something that you need to have seen before in order to apply it. It's not the kind of thing, it's a very new, not new technique, it's not a new technique, it's just something I haven't really done in any of the questions so far. I'm going to multiply top and bottom of this fraction with a particular quantity, and the quantity is 1 minus sine x. And the reason I'm doing that is because I know that's going to work. This kind of technique is also used in integration if you have to integrate things not that look like this, if you have things that look like this, so you cannot split the fraction. So what will happen when you do that, and why do I do this? This is of course a difference of squares, or you can take your time and multiply it out. But whatever you do, you're going to get 1 minus sine squared of x. And at the bottom, I'm not going to multiply anything. I'm going to leave it as it is. This, of course, is the cos squared of x. So this is, I'll write it here actually, probably better. So that's equal to the cos squared of x, that's the numerator. And cos x, 1 minus the sine of x. Okay, I can cancel the square, so this leaves me now the cos of x on the numerator over 1 minus the sine of x on the denominator, which of course is just the right hand side. So this is something new that we haven't seen before, but it does work. The same way if you started from the other side, so you started with cos x over 1 minus sine x, you would have multiplied top and bottom by 1 plus sine x this time. That's if you started the right hand side to the left. It will work in a pretty much the same way. Okay, I hope you find this useful. I'm going to do one more lecture, and that's enough really for trig identities. I hope you copy with the harder proofs now, and next and final lecture number 4 is going to be slightly harder than today, and you find it useful and you pick up skills. Keep practicing, and all I'll say is, who's laughing now? Well, we are, because hopefully we are getting better. Okay, bye.